So before anything else, let me introduce to the topical workbook for computer science 2210 or 0478. This is the workbook 1 for paper 1, basically computer systems. And as you can see from the table of contents, I've included questions on each and every subtopic from the syllabus along with the mark scheme. And these are some of the actual questions, actual pages as a preview from the workbook. Section 1.1, 1.3, 2.2, 3.2, 5.3 cybersecurity and artificial intelligence. This is just to show you a glimpse of what type of questions are included in the workbook. There are many more questions where these come from, and around 18 to 20 questions on an average are included for each and every topic. A must buy if you want to boost your grade. Similar to the paper 1 workbook, I have designed a paper workbook for paper 2 as well. This is for algorithm, programming and logic for CIEs either 2210 or 0478 GCE or IGCSE Computer Science. As you can see, it contains questions on every subsection of the syllabus content for paper 2 along with the mark scheme, so you can understand each and every question, each and every algorithm. These are some of the few pages from the workbook just to give you a glimpse of what type of questions are included. As you can see, this is 7.1, this is 7.7, 8.3 and section 10 Boolean logic. So a lot more questions are included in the workbook. A must buy if you want to have a very good score in your Cambridge examination. Order now. Assalamu alaikum warahmatullahi wabarakatuh. Welcome to another physics lecture. So today we are going to start section number 3, that is named as waves. And we will start our discussion with section 3.1, that is the general properties of waves. Now the first thing you need to remember about waves is that waves only transfer energy and information in the context. They do not transfer matter. They are described as oscillations or vibrations about a fixed point. For example, ripples cause particles of water to oscillate up and down. There are two types of waves. One is known as transverse waves, and the other ones are known as longitudinal waves. What are transverse waves? The waves that travel in the direction perpendicular to the direction of vibration or motion. The direction of motion of the wave is perpendicular to the direction of oscillation. For example, ripples in water, electromagnetic radiation, and seismic S waves or secondary waves. The energy transfer is in the same direction as the wave motion. They can move in a solid, liquid, but not in a gas. Some transverse waves, such as electromagnetic waves, can move in a vacuum as well. The highest position in a wave is known as a crest or a peak, whereas the lowest below the average position is called a trough. Whereas pressure in transverse waves remains constant. We can see how a transverse waves is by tying one end of a rope to a fixed point and then moving it up and down. This would create a sine wave like pattern that is known as transverse waves. This is the vibration or movement of the particles, whereas this is the movement of the energy, or this is the direction of the motion. As you can see, these both are perpendicular to each other. The next type of waves we have are known as longitudinal waves. They travel in the direction parallel to the direction of motion. There are areas of compressions and rarefactions inside this wave. Sound waves and seismic P waves or primary waves are an example of longitudinal waves. The energy transfer is in the same direction as the motion of the wave. Always remember, energy transfer inside a wave is always in the same direction, no matter what type of the waves. Longitudinal waves can travel in solid, liquid and gases, but they cannot move in vacuum as there are no particles. In a longitudinal wave, when points are close together or when particles are close together, it is called a compression, whereas the part of the longitudinal wave where particles are away from each other is known as rarefaction. In a longitudinal wave, the pressure keeps changing because particles keep on compressing and expanding. We can understand longitudinal waves by pressing and releasing a spring. This is a spring. The part where the coil is close to each other is known as the compression, whereas the part where the spring is expanded is known as the rarefaction. Whereas the direction of the motion and the direction of energy transfer would be the same, and as you can see, the direction of motion and the direction and the vibration of the particle would be the same. Inside a sound wave, inside a longitudinal waves, the particles vibrate from left to right or in a horizontal position. Now there are some key terms or key components of waves that you should know. Crests and troughs. A crest or peak is the highest point on a wave above the equilibrium. This part. The trough is the lowest point on a wave below the equilibrium. The period is the time taken to produce one complete wave. One complete wave means from here till here, or from one crest to another crest, from one trough to another trough. Normally we make one wave like this. SI unit for time for period is seconds, and the formula is T equals to 1 upon F. Velocity, the displacement of wave traveled in 1 second. SI unit is meter per second square, and the formula is supposed to be V equals to F lambda. Lambda is supposed to be this symbol, and it is supposed to be the wavelength. Wavefront, an imaginary line connecting all points in the same phase. Amplitude, the maximum displacement from the rest position to the peak of the trough. SI unit is meter. A wavelength, denoted by lambda, the distance between two successive peaks or trough. SI unit is meters. Frequency, the number of complete waves passing through a single point in 1 second, or the number of complete waves generated or produced in a second. The SI unit is hertz. A wave speed is the speed at which energy is transferred through a medium. It is defined as the distance traveled by a wave per unit time, or every second. It is measured in meter per second. It can be calculated using speed equals to frequency into wavelength. And as you can see in the images, this is the mean position, or this is the normal position, whereas the distance a wave rises from the normal position is known as amplitude. The distance between one crest and another crest, or one trough and another trough, is known as a wavelength, whereas a wavefront is supposed to be an imaginary line that connects points on a same line. Like if I draw a line from here till here, then all the point that would come in this line would be in the same phase, or they would be having the same wavefront. So if I draw a line like this, so this point, this point, this point, and this point, all of these points would be in the same phase, and they would be in the same wavefront. And over here, this is supposed to be one complete wave, and the time it takes to produce one complete wave is known as period. Whereas frequency is supposed to be the number of complete waves that are produced in 1 second. If you have a higher frequency, you'll have more waves being produced per second, whereas lower frequency means less number of waves are produced per second. If the period is high, then wave pattern is like this, means lower frequency, whereas if period is low, then the more waves would be produced per second. In all cases, wave transfer energy without transferring matter. For water waves, this means it is the wave and not the water that travels. The water particle stays in their position, whereas the energy or the wave is transferred ahead. For sound waves, it means the wave and not the air molecules travel. Objects floating on water provide evidence that wave only transfer energy and not water. Now let's discuss an example question. The diagram shows a loudspeaker that is producing a continuous sound wave of frequency. This is a loudspeaker. This is a point P. Which diagram best shows how the sound wave causes a molecule at P to move during 1/200 seconds? This is basically the time. This is basically the period, 1/f. So 200 would be the frequency. But over here, basically, we simply have to state in what direction the molecule is moving. Since this is a sound wave, and sound is a longitudinal waves, and we have discussed in longitudinal waves, particle move from left to right. So our answer would be A. B cannot be the answer as particles are only moving in one direction, whereas D cannot be the answer because particles are moving up and down. This would be the answer if it was a longitudinal wave. Figure 4.1 shows a wave on a rope and 4.2 shows a wave on a spring. Both waves are moving in the direction shown by the arrow, this direction. State the name of each of the two types of wave. 4.1 is obviously a transverse wave, whereas 4.2 is a spring, so it would be a longitudinal wave. Draw a wave which has a smaller frequency than the wave shown. For showing a smaller frequency, we would dilate the curve like this. Right now it is showing 1, 2, 3, 4 complete waves. So draw 2 or 3 complete waves less than 4, something like this. Something like this. So that the frequency would be less. Lower frequency means less number of waves produced. So simply extend the wave like this and it would be a lower frequency. Wave drawn with larger wavelength. Wavelength is this distance, so simply draw it with a larger distance. Describe the movement of point X on the spring as wave passes. Point X is inside a spring, so it would be moving from right to left, backward and forward, or left to right, to and fro, however you want to describe it. The vibration would be parallel to direction of wave or direction of motion. So we'll keep it till here today. I'll see you guys in the next lecture and we'll continue with this. I hope you have understood everything. Take care. Allah Hafiz. Please do let me know your comments and feel free to contact me if you have any issues.